So in Chapter 8, we talked about similarity properties. We talked about it in terms of triangles, quadrilaterals, random shapes, and we solved them by using ratios and proportions. In this most recent stuff of Chapter 9, we've looked at how to solve different kinds of right triangles using trig. Well, we're going to take a step back to Chapter 8's proportions and ratios, but we're going to use them particularly for special cases of right triangles. So let's take a look at this definition. If the altitude is drawn to the hypotenuse of a right triangle, then all three triangles are similar by angle-angle similarity. So you could think about this as breaking the big triangle down to be a small, a medium, and a large, or just labeling them as triangles 1, 2, and 3. So what I've shown here is that if you look at this big one, that's that big triangle, big one here, or I call it here BAC for large. I could also take this medium portion and that smaller portion. So that gets me this triangle CAD and that other triangle BCD. Now, I know that they're going to be similar based on several properties of triangles. Remember that all angles add up to 180. Notice that if all of these triangles has a right angle, 90 degrees, and they're similar, then the other two angles are the same. Now, it doesn't matter what those angles are as long as we can demonstrate that they have to be the same. And that's what I call the dot arc method, because I label my angles using dots and arcs. So notice in this big one here, so I started with this, and I said, okay, here's my right angle, put down a dot, make this other one be an arc. Let me go ahead and get another color out. So I'm using red for my dots, I'm going to use green for my arc. So red for dot, green for arc. In the other two, I said, okay, well, this is going to be a dot, and that's a dot. Again, doesn't show up the best here because I already have the black ink behind it. It'll show up better when I do my example down below here. Green for arc, green for arc. And you might ask, well, how did I know that was an arc and that was an arc and these are the dots? We'll come back up to here. In this big triangle, I have right angle, red dot, green arc. If I look at this triangle right here, there's my right angle. There's my red dot. What I'm missing then must be a green arc. Or take a look at that right-hand triangle. My right angle is at the bottom here. I have a green arc. What I'm missing is a red dot. Notice here that a right angle is then the sum of the green arc plus the red dot. Whatever measure they are, doesn't matter. This property will always hold. Let's look and see how this works better with this triangle down here that has nothing else labeled on it. So I'm going to start with that dot arc method, and I'm going to keep it red dots, green arcs. Notice this big triangle here. Just to make this easier, I'm going to start by putting a red dot on the very top and a green arc down here. So red dot, green arc. Also right now, notice that I have this right angle right here. Let's go ahead and extend that over to here because technically it's sitting on that side as well. Right now, I'm going to go ahead and fill in this one. I'm going to take this triangle to match this one right here. So this is O, M, N. Let me rearrange that here. O, M, and N. I'm having that match it from right here. Okay, I'm going to go ahead and fill in that based on this labeling, this is my red dot, and right here is my green arc. Okay. All right, well, take a look at this one here. Notice this little right angle here? That's my red dot, and in any triangle, they must always add up to the same. If the big one is red, green, and 90, this smaller one is also red, 90, and green. So let me come up to here. Let's make this one be my red dot. Let's have that next one be my green arc. And let's go ahead and label it now. So in this top triangle, the red dot matched O. The 90 was P. And the green arc was M. Let's look at the final remaining one here. Go back and recenter that. I have my right angle. I have my green arc. What I'm missing is that red dot. Let's go ahead and fill it in. That red dot belongs there. Here is my green arc. Go ahead and label the letters now. So red dot in this bottom triangle was at point M. So here's M. The 90 degree happened at P, and the green arc, that was N. So notice that I've now arranged them all so I can tell how they're similar. So when I'm coming through now, and I'm going to go ahead and label these, I've got triangle OMN, similar to OPM, similar to MPN, and these are always going to be similar by angle, angle, similarity. Now again, similarity means of a ratio that can be applied, a scale factor, to get from one triangle to the next. Another way to view this, it might have been easier if you'd color-coded the sides. Again, that is up to you. I'm showing it purely using dots and arcs. Go ahead and do that same thing for this bottom one here. So coming through, notice that I have this big figure here. I'm going to take that big triangle and make it this one at the bottom. So let's start that. Here is L, here is M, here is K. So L, M, and K. Notice that up here is my right angle for L, M, K. Let's go ahead and write that on in. And I'm going to put this as my dot. So L is dotted, like that. And then that makes my K being the green arc, like that. Because again, dot, 90, arc. When I'm doing that big triangle, I'm ignoring that altitude going down the middle. Now, as we talked about in chapter 6, so a couple months ago, an altitude goes from a vertex to the opposite side, and it forms a right angle. So it's perpendicular to the opposite side. It is not bisected, not necessarily. All it means is it cuts it at a right angle. It does not tell you where along the line it does the cutting. So red dot, green arc. Okay, let's go ahead and do this one over here. So notice that in this triangle, here's my right angle. Here's my red dot. What I'm missing then is the green arc. So here should be a green arc. Let's put that one right here, backwards here. Here is my 90. Here is my red dot. Here is my green arc. Okay, I'm gonna go ahead and label those parts. So this one here is L. The 90, that was at N. And the green arc, that was at M. Okay? Let's do the same thing for that small triangle, remembering that wherever there's a right angle, it continues on that other side. So this top angle up here, again, is our right angle. We're labeling that one to be N. Let's come back up to our picture here. I have right angle, green arc. This then must be the red dot. So over here, I've got red dot, and then I have green arc. And I'm going to go ahead and label it now. The red dot happened at point M, and the green arc happened at point K. So we're now ready to go ahead and write down these triangles for their similarity statements. I'm going to choose M and K, which will have to match L and M, L and M, and finally L, M, K, L, M, K. And the reasoning is always going to be angle, angle, similarity. So the reason why we're doing this, which will become a bit more apparent on the next page, is that we are setting them up so we know how they're similar. Now that we know how they're similar, we can make some sort of statement about finding missing sides because we can create ratios. Now, right now we have no numbers, so it's not too exciting. But on the next page, I'll show you what it looks like using just variables and locations, and then we'll actually solve for sides. Okay, so in this example, I have this big triangle here, and in the positions of the side lengths, I have different variables. Now you can see what will happen when we actually give numbers for these things. So I'm going to start as before. I've been using my dot arc method. So I'm going to go ahead and make A be a light blue dot. There we go. So I'm going to use the big triangle first. Light blue, 90, arc. So B is going to be my pink arc. Taking a look at the small one now. Light blue dot, 90 degrees. What I'm missing up top then is the pink arc. Here we go. Pink arc. Looking at this far one over here, 90 degrees, pink arc. What I'm missing is light blue dot. And again, notice dot plus arc gets you the right angle. So for these ones down here, I'm going to pick a pattern and stick to it. Looking at this, let's go with the small triangle. Notice that the arc is opposite the shortest side. So let's keep with that. In these pictures, let's have the arc be opposite the shortest side. So let's put the arc here, here. Let me slide it up for a moment. Down here. If I do that, then my light blue dot is at the top of each triangle. So light blue, light blue, light blue. Okay. So let's go ahead and start with the small triangle. Looking at our figure, that is going to be the smallest triangle. And if you need to, label it as small. So looking at that smallest triangle, between my dot and my 90, so dot and 90, I have X. Between dot and 90, I have X. For dot to arc, I have B. And I am trying to color code this right now. I have B. From 90 to arc, I have H. There's my H. So I now have that small triangle marked out with the sides. Let's do the large triangle. Dot to 90. So in the big one, again, this big figure here, dot to 90, that's B. I'm now going to do 90 to arc, which is A. 90 to arc, so A is down here. My last side is along here, dot to arc, dot to arc. Notice the sum of the dot to arc is X plus Y. So X plus Y. So that is it for the large. I'm going to go ahead and do the same thing for the medium. So medium is down at the bottom. The nice thing about the medium is the way I oriented this. It perfectly matches this right here. So that diagonal dot to arc, that's my green A. Looking at my altitude here, dot to 90, that's my H. Dot to 90, that's my H. And then finally along the bottom, that was my Y. That's my Y. So now, just looking at the way we have organized these here, notice that I can now make comparisons. I know that B, X, and H are similar. X plus Y, B, and A are similar. H, A, and Y are similar within their respective triangles. So right now, I still don't have any numbers, but this kind of helps you see where I'm going with this in my next step. I'm going to be comparing triangles and using that information to figure out missing side lengths. So for this next triangle, this time we're going to be actually solving for the variables, but the process is still the same. I'm going to start by noting the dots and the arced angles. So looking at this here, I'm going to look at this big one, and I'm going to go ahead and put my dot in this corner here, and I'm going to put my arc in the top up here. So here's my arc, there's my dot. Let's take a look at this bottom triangle now. Here's my 90, here's my dot. So this one right here must be the arc, just like that. And remember here that when I have that 90 up top, it really extends into that next box like that. So in that top right triangle, I have dot and arc, and what I have 90 and arc. What I'm missing is the dot. So here's my dot right there. Okay, well, now I'm going to go ahead and I'm going to redraw those three triangles. No, they don't need to be to scale. It could be helpful, but it's not necessary. And I'm going to draw them all with respect to this large triangle. So that's the direction I'm going to draw mine, just so I make fewer mistakes, we hope. So I'm going to go ahead, go through here. I'm trying to label them. I'm going to draw them all the same way, and then I'm going to go ahead and label them next. Okay, and this time I'm not labeling them with the points, but I am going to label them in terms of dot, arcs, and 90s. So in this big one here, that was my 90. Actually, let me pause right now. Before I actually put stuff down, let's just mark all the angles on here. I want all of my triangles to be oriented the exact same way. So the red dots will all go in the bottom left. My green arcs will all go top right. Okay, and the first one I'm going to do is going to be for this big figure here. All right, so if I'm using that big triangle, notice that this bottom side is my y. Notice that my height is c. Notice that my hypotenuse here, this diagonal, is the sum of 16 and 9. So if it helps, make yourself that little note. I'm going to add them up when I go across to get 25. So this here is 25. I'm now going to go ahead and take a look at this bottom one. I'm going to do this bottom one here, and then this one over there. So in this bottom one, dot to 90 is 16. So dot to 90 is 16. 90 to arc is x. 90 to arc is x. And then I'm missing dot to arc, that's y. Do the same thing for the far right triangle coming from right here. Dot to arc is c. Arc to 90 is 9. And then lastly, dot to 90, that's x. So now that I've gone ahead and labeled them like this, I'm now able to make some proportions. Now, to be fair, they might not be as nice of proportions as you would like. That's definitely what might be happening here. But I'll still show you how to work with it. So in Chapter 8, our proportions had 3 numbers and then probably just one missing variable. Well, right now we might have something a little bit more complicated, but it's still done in about 2 to 3 steps. So for the first one here, notice that if I take a look at these 2 triangles and I look at the hypotenuse and the right side, I have 25 and c. I have c and 9. So I have the same variable twice, even though they don't perfectly match up. I'm going to go ahead and use that to make my first proportion. I have 25 over c equals c over 9. So I did hypotenuse over far right equals hypotenuse over far right. And I am going to go ahead and I'm going to cross multiply right now. So remember, cross multiplying looks like this. Coming along that direction, and I'm going to come along that direction. So c times c, let me actually draw another arrow. I'm going to go this way. C times c is c squared. 9 times 25, well, that's going to be 225. So I have c squared equals 225. I want to solve for c. Do that by taking the square root. Remember, square root and square, they're going to go ahead and cancel. So at this stage right here, I'm going to go ahead and come through, and I'm going to take the square root of both sides. So I took the square root of the left and of the right, meaning that c equals 15. You might say, oh, how do you know that? Well, the square root of 225 is 15. Don't believe me? Plug into a calculator. Square root 225, 15. Okay, so we have found c. Let's go ahead and label that on our diagram. So all of the c's, they are all 15. Well, guess what? If you take a look at those triangles, we can now use Pythagorean theorem to solve for the rest. Remember Pythagorean theorem, let me actually write that up top here. Pythagorean theorem. We can use this to find missing length of right triangles if I know 2 of the other lengths. So a squared plus b squared equals c squared. I can use that now. Take a look at this one right here. I have 15 and I have 9. I can solve for x. And because again, that c we just found, let me actually put it back in my figure here. That's this one right here. So that's 15. Okay, so I'm going to go ahead and I'm going to solve for x right now. So I'm going to use this one right here. Let me kind of separate it here. I've got x squared plus 9 squared equals 15 squared. Side squared plus side squared equals hypotenuse squared. So I have x squared plus 81 equals 225. And again, I'm going to go ahead and subtract I'm going to subtract 81 to the other side. So 225 minus 81, and I get 144. So again, I'm moving it over to the right-hand side. So what I've got then is x squared equals 144. And I say, oh yeah, well 144, that's a perfect square. It's one we've used on our times tables. X is 12. So again, so far, we have found that c is 15. We have found x is 12. We'll come back through and label what we found. So this x here, that's 12. This x here, that's also 12. We're missing just one more, and that's going to be to find y. So I'm going to go ahead and do the same process over here. To do it for y, I'm going to do it in this one right here. So this time I know that x is 12. So I'm going to do 12 squared plus 16 squared equals y squared. 12 squared is 144. We just used that a moment ago. Oh, I feel like that's kind of reflective there. 16 squared is 256. So plus 256 equals y squared. We're going to go ahead and add them together. So 256 plus 144 gets us 400. So 400 equals y squared. We're going to go ahead and take the square root of both sides. So here and here. And the square root of 400 is 20. So we have now found all of the missing values. And again, to prove it to you, square root of 400 is 20. So if you wanted to check your work, you could use Pythagorean theorem on each of the triangles and make sure they all worked, basically. You found the value of c to be 15, x to be 12, and y to be 20. We're going to go ahead and try this now for the next question. So in this next picture, I'm going to go ahead and start the same way. I'm going to dot and arc my angles. So I'm going to make this one down here be my red dot. I'm going to make this far one be my arc. And again, I'm doing it that way just so I'm starting by labeling it based on the biggest triangle. So this big triangle uses everything. Here's the right angle, red dot, green arc. Now let's take a look at that medium-sized triangle. Red dot, 90 degrees, green arc on top. And then for that small triangle on the right-hand side, 90, green arc, red dot. And again, our job is to go ahead and find the missing variables. So right now, I'm going to go ahead and copy those triangles off to the side here. And I'm going to do them all, let's see. I want to do them based on, let's do it based on the way this one faces here. Doesn't matter, just be consistent whatever you choose. I'm going to have everything face the same way as the medium. Which means that these bottom corners will all be 90s. I'm going to put red dot on the far left. And then finally, green arc, top right. Okay. All right, so let's go ahead and label those sides. Actually, let me switch colors here. Alrighty, so if I start this one off based on the medium here, y is over here, 9 is on the bottom, C is going up. So that's based on that medium triangle. Let's take a look at the small triangle. Arc to 90 is 2. Arc to 90 is 2. Dot to arc is x. And then finally, dot to 90 is C. Let's go to the large triangle, this really big one here. Dot to arc, all the way across here, that's 11. Remember, I'm adding 9 plus the 2 to go all the way across. So dot to arc is 11. If I do dot to 90, that's going to be y. If I do 90 to arc, that's going to be x. So I now have these triangles, and I'm going to go ahead and say, do I have enough information to solve anything immediately? I have one number, one number, one number. So I can't use Pythagorean theorem yet, but I can use ratios. So looking at this, again, you can choose which ones you want to deal with. I am going to look at this far side. Let's see, which one's going to be best? I think I want to do these here. So I'm going to do C over 9 equals 2 over C. That's how I'm going to start. C over 9, that is a 9, equals 2 over C. And I'm going to go ahead and cross multiply. When I go along this diagonal here, I get out C squared. When I go along this one here, I get out 18. Now, I do want to go ahead and simplify that once I take the square root. So I'm going to go ahead right now and take the square root of both sides. And again, I'm dealing with distances, so I only want to use the positive square root, not the negative. So I have C equals the square root of 18. Now remember, square root of 18 is the same thing as root 9 times 2, because that is what we started with here. And we know the square root of 9 to be 3, which means really C equals 3 root 2. That is the first value we found. C is 3 root 2. So on my diagram right here, I have 3 root 2, and I have 3 root 2. Well, guess what? We now have enough information to use Pythagorean theorem. Let's take a look at this one right here. So let me go ahead and separate that. So I have 9 squared plus 3 root 2 squared equals y squared. Okay, 9 squared is 81. 3 root 2 squared, so I'm going to square both parts. I'm going to square the 3. I'm going to square the root 2. 3 squared is 9. Root 2 squared is just 2. Remember, the square and the square root cancel out. This equals y squared. So right now what I really have is 81 plus 18. Again, 9 times 2 here, that's my 18. So 81 plus 9, that's going to be 90. Plus another 9, I have 99. So y squared equals 99. I'm going to take the square root of both sides. So y equals, and that 99, let's think about that as 9 times 11. And I'm doing that so you can see how it's going to break down. The square root of 9 is 3. So really what we have is y equals 3 times the square root of 11. I'm going to go ahead and block that off. We have now found y. So again, y is 3 root 11. This y is also 3 root 11. We have one thing left to find, and that's going to be x. Let's go ahead and use this pattern right here. So using this one here, I'm going to have 2 squared plus 3 root 2 squared equals x squared. Just like that. 2 squared, that's 4. 3 root 2 squared, well, we already did that. We said it's going to be 9 times 2. Again, 3 squared is 9. Root 2 squared is 2. So 4 plus 9 times 2 equals x squared. Now 9 times 2 is 18, and 4 plus 18, that is our 22. So x squared equals 22. Let's go ahead and pick a different color here. Let's go ahead and take the square root of both sides, which means that x equals the square root of 22. And nothing simplifies, so that's going to be my final answer. So we've found the 3 variables. The first one I found by using the proportions. The next 2 I did by using Pythagorean theorem. And I kept my answers always simplified in radical form. If you want to go back, I already have notes on that in a previous section. We have one final question here. I'm going to go ahead and start by marking off the dotted and arced angles. So I'm going to put my red dot right here and my green arc on that far opposite side. And again, I'm doing this based on that big triangle. Here's my 90 degrees, red dot, green arc. If I look at this one here, here's my green arc. I have a 90 automatically sitting here. So this one is a red dot. If I come over to here, red dot and 90, so I must have green arc sitting right there. And if you're somebody who likes to see the 90 sitting there, just go ahead and draw it right in. Okay, I'm going to go ahead now and draw out the triangles. And I'm going to draw these triangles relative to this medium over here, just because I like the orientation. So here, put down a small, try to get a larger one out, and then finally the biggest one yet. Okay, so based on this, I've put all my 90s right there. I've put my red dots all in the bottom. So red dot, red dot, red dot. Then I'm going to go ahead and put down my green arcs. Green arc, green arc, green arc. Okay, so this one here is the medium, just small, medium, large. If that's the medium, it's going to match perfectly with what I have sitting right there. Which means that this one is 6, this one here is C, and the top is A plus 4. Okay, let's take a look at the small. Dot to 90 is 3. Dot to 90 is 3. 90 to arc is 6. Dot to arc is B. Make sure your B's and your 6's can be told apart. Now for the large, the big one here. So in this big figure, here's my 90. 90 to dot is B. 90 to arc is C. So 90 to arc is C. And then dot to arc is 3 plus A plus 4, which is A plus 7. Remember the numbers, I can just combine. 3 plus 4 is my 7. So all the way across here, that's my A plus 7. Okay, so before we do any ratios, let's take a quick stock of what we have. Check each triangle. In any of the triangles, do we know the actual value of 2 of the sides? Yes. In the small triangle, we have a 3 and a 6. We can actually start by using Pythagorean theorem and solve for B. And it's entirely possible we might not actually need any special ratios to solve this question. Let's see what happens. So again, I'm going to solve for B right now. I'm going to say B squared equals 3 squared plus 6 squared. So I have B squared equals 9 plus 36. So B squared equals 45. I'm going to go ahead and take the square root of both sides. Okay, so right now I have B equals the square root of 45, but again, think about what it means to break that down. 45 has a perfect square inside it, 9 times 5. So B equals the square root of 9 times 5. And again, I'm telling you that because this way it's much quicker to break down. I can see the perfect square. The square root of 9 is 3. So b equals 3 root 5. That's our first value. Let's go ahead and block that off. So again, for b, we already know it's 3 root 5. And we come through and check now. Do we need to do anything else special? Yeah, we do, because we still don't know the value of c or a. Okay. Well, looking at this, the next one for us to do, I'd say, let's do this one here. Let's do 3 to 6, 6 to a plus 4. So let me go ahead and switch colors here. So we are going to use a ratio after all, but it should be pretty painless. So again, I'm doing 3 to 6, so left to top equals left to top. 6 over a plus 4. And as I told you guys when we first taught this in Chapter 8, so again, we actually did this one in class, there's a couple ways to do it. If you are very good at cross multiplying and you want to use that, you can go right ahead. You can also simplify the fraction first if you prefer. You can also compare them and see what you need to get from one to the next. I'm going to go ahead and show it though with cross multiplication. Any of those methods are fine. So I'm going to do 3 times a to get 3a, 3 times 4 to get me 12, equals 6 times 6, 36. Now again, the one thing to be super careful of, when you're cross multiplying, that 3 goes to the a and to the 4. That's why I got 3a plus 12. From there, simplify the linear equation. Subtract 12 from both sides. We get 3a equals 24. Divide both sides by 3. A equals 8. I'm going to go ahead and block that one off. So that was a nice one. No radicals, pure number. So a is 8. Now again, if a is 8, think about that entire side length. This entire side length now is 15, because 8 plus 7. And this one up here, 8 plus 4, this one is 12. Now we have to solve for c. It shows up in 2 of the triangles. So the question is, which one is easier? In this one, I have a side of 6 and 12. In this one, 15 and 3 root 5. Well, this one will be easier because there's no radicals, just integers. So I'm going to highly recommend you use that one for your equation, but it is up to you. You'll get the same answer in the end. So again, I'm going to use this one right here. I have c squared equals 6 squared plus 12 squared. So I have c squared equals 36 plus 144. And I'm going to go ahead and put them together. So I have here 144 plus 36 to get 180. So c squared equals 180. I'm going to go ahead and take the square root of both sides. Okay, so as I do that, coming down to my next line here, I have c equals, and I say, okay, well, what do I really have here? Remember, I know 18. 18 is 9 times 2. So 18 times 10, well, that's 9 times 2 times 10. Let's go ahead and start with that. Square root of 9 times 2 times 10. Now, that 10 is really 2 times 5. So I have c equals square root 9 times 2 times 2 times 5. Well, let's go ahead and simplify that. 9 is a perfect square. These 2's put together are a perfect square. So my final value for c, the 9 comes out to be a 3. Those 2's, think about it like 4, if you prefer. They are going to leave the radical. One's going to come outside. So times 2. And what has to stay inside is the 5. So 3 times 2 is 6. So 6 root 5 is my final value for c. Say that here. That equals c. Okay. So we've now gone ahead, we've used Pythagorean theorem and a ratio to solve for those missing variables. So everything in this section about using those similar right triangle properties, your first step, label the dotted and arced angles, whatever symbol you want. After that, I highly recommend picking a direction to use. Make 3 triangles, can be the same size or different, doesn't have to be to scale. And then label the marked angles, then go ahead and put down the missing side lengths. From there, figure out what do things have in common. If they have pure numbers, like these here, that'll be easiest. If not, create a ratio, like we did here, or even here. That way when we cross multiply, I can solve for the variable. Now, if you do have one like this, where they don't perfectly match up, the key is that the variable across from each other diagonally must be the same. I can't have 2 different variables in the same equation. I can only have one. But as long as those conditions are met, you can solve for all different side lengths in these similar right triangles.